Thank you all. It's a pleasure to be here. I'm kind of new to the human AI game, so all the research I'm going to tell you about today is hot off the presses. As a matter of fact, not even yet to the presses. So any feedback you have, I'm happy to talk about this artwork. I also appreciate, I see a number of attentive faces, which is very impressive given the late hour and the unbelievably freezing quality of the room, but thank you for doing your best to pay attention. I'll do my best to stay awake as well. I'm a psychologist. One of the things I'm interested in is metacognition, the ways in which we know about the knowledge that we have and the ways in which we go about remediating failures of our own bases for knowledge. This question about metacognition and what kind of role it plays in our everyday intellectual lives shows up as well in group cognitive tasks. I'm going to start by telling you about that, but I also I always insert my my collaborators at the beginning to make sure I don't run out of time for them at the end. In this case, the three primary collaborators on the three projects that I'm going to try and rapidly shove down your throat over the next 14 minutes are Belgian Unal, who was a student of mine at Illinois and is now at the University of Michigan, and Will and Zheng Feng, who are both current students at the University of Illinois. So I want to start just by talking a little bit about what humans do when they work together. We're going to work our way up to the problem about human-AI interaction. But there's an important lesson about human groups that I want to start with. If you ask people, particularly people in the judgment and decision-making world, why groups outperform individuals, and by the way, they do outperform individuals on an impressive variety of tasks. I think I have a short list of some examples coming up. One of the things that people will point to, and I think the thing that has generated the most voluminous research on the topic, is the idea that multiple humans together possess more knowledge than single humans. We see this in the wisdom of the crowd literature, where aggregating responses from a variety of individuals leads to impressively accurate responses, often more accurate than you would ever expect from any individual from the bunch. This shows up not just in historical tasks about judging the weight of oxen, but also all kinds of modern problems, in this case, say, identifying misinformation, identifying phishing websites, things like that. So there's lots of implications for how groups are doing this. But what I want to point to is something that's often lost in this group cognition literature, which is that groups perform better for another reason. And it's because they have the opportunity, even in short exchanges, to trade with each other information about the information that they hold. They don't just say what they believe, they also say something about why they believe it and the confidence that they hold in it. And it turns out that's a really, really critical part to how groups work well together. I'm going to tell you about one example of that from Belgian Unal's dissertation. In this experiment, is there a laser on here? No, okay. In this experiment, there are two groups. There's one in which people are performing this task individually. There's a variety of tasks. The one that I'm illustrating up here is, you can see general information questions that are two alternative forced choice like this. These individuals answer the question, and then they give their confidence assessment in that answer. What we're going to do is we're going to create sort of fake nominal groups out of combining individuals from this individual condition, sometimes just by averaging things. We can't do that here because there's no numbers to average. Sometimes by randomly picking answers, and sometimes by choosing the more confident out of a pair that didn't really get to work together, but we can pretend that they did. And we're going to compare that. All right, we're going to compare that to a group that's actually working together. And when I say working together, this is pretty minimal working together. So often the time they will spend talking about each one of these questions is on the order of 10 to 15 seconds. This shows the distribution of performance when you randomly, so you take two random people from the individual condition, you put them together in this nominal group, and then you create a metacognitively naive baseline, what we're calling here no information sharing, where we just grab a random answer from one of them for each question that's in the pool. I can't remember, I think there's like 60 questions or something like that. And this is what the distribution of scores looks like when you do that. You can see the mean is, I have a hard time from this angle seeing what it is. It's a little below 0.7. We're going to compare this now to a nominal group in which, instead of doing that, we have a metacognitively sophisticated group in which we take the more confident rating among the two. So we have two people together. For each question, we just see who is more confident in their answer. That becomes the answer. The number of correct answers across the group becomes the group score, and you can see that group does better. Okay? This tells us that their metacognition is tuned, that this is part of what happens when people answer questions correctly and share information with one another, is that they can share their confidence, and if they choose to simply to elect the person's response that holds the higher confidence, they'll get a big boost in performance. I know it's hard to see, but when you use these kinds of distributions, the effect sizes of this are very, very large. Everything I'm going to show you in this study is between Cohen's d's of greater than 0.6 and often near 1. Now, critically, we're going to compare this to the condition that actually got to interact. If all they do in the course of interacting is relay univariate confidence information with one another, then it'll look just like that, whatever that color is, yellow condition. But in fact, they do yet better. 10 to 15 seconds of a brief exchange about a dumb question like this, where you would think that there's not that much to talk about, leads to a huge increase in performance, even over a metacognitively sophisticated, plausible, controlled nominal group. So why is that? There's a couple things. I'm not going to get deep into them. Anyone who's interested, I'm happy to follow up later. But you can, for example, listen to the quality of the explanation by which someone comes to their reasoning and decide, oh, well, I buy that, or I do not buy that. And that can be a basis for continuing to argue further about what the right answer is. Confidence itself can be multidimensional. Questions like this require you to have multiple bases for knowledge. You might have high confidence in one thing that you believe, but low confidence in another. This allows you to mix and match different parts of a person's response and figure out what the conclusion would be if you share partial information that way. I'm going to talk real briefly about calibration, which is a really important part of this. Calibration is the quality of having confidence ratings that are meaningfully predictive of accuracy. And in group cognition, it's even more important that not only are they predictive of accuracy, but that you and your partner use the same scale. Keep this in mind. We're foreshadowing what's going to happen when we start talking about human-AI interaction. When we look at calibration, we often look at it on a function like this, which is simply plotting bin confidence and the accuracy at each of those levels of confidence that's expressed by the human. One of the interesting things that came out of this study that I showed you, something we were not originally looking for, but was a pleasant surprise. If you look at that blue line here, so bear in mind, lines that are closer to that red diagonal, which is perfect performance, is going to indicate better calibration. Groups are actually more calibrated than individuals, considerably more calibrated. That's actually a really big effect for this kind of literature. So not only are groups more accurate in the decision making, but they are also going to be more well calibrated in the way they express the products of that decision making to one another. Okay, brief interactions, as I showed you a minute ago, help you exchange metacognitive information and also allow you to calibrate confidence assessments both to reality and to one another. Now, back to the star of the show, AI. This is a fun Substack article by Helen Toner. People in here read her? She's great. She writes a lot about AI policy and things like that in Substack. This is now an older piece, older in your world, not in psychology world. It's like 3 months old. And in listing a set of what she called intractable issues about AI, she lists as a really primary one this idea of overconfidence. You ask a question, they have no idea when they should say, I don't know or I know. They're not very good at recognizing if they've made a mistake and backtracking. Of course, we've heard this come up again and again in the talks we've seen today, both in the ones that I heard on the other side of the room and in here today. The metacognitive capacity of these agents is incidental. I would say sometimes they're good at doing this, but it certainly doesn't possess any specialized bespoke capacities for conveying the kinds of information you would need to be a good teammate to a human that's going to rely on confidence assessments. So the second part of the project that I want to tell you about today is about mechanisms for scaling confidence from AI systems. And I'm going to simplify things a little bit. We're not going to talk about LLMs. We're going to talk about this in the context of convolutional neural networks, which are still solid models for computer vision kinds of problems and for classification in general. I'm not going to tell you about the many things that we compared in this analysis, but I want to tell you about a particular style of approaching this problem. So if you read in this literature, I would say the most commonly used approach is some combination of softmax scaling at the output layer. You know, you just take the different competing options at the output layer, use a softmax transform that, often with a temperature scaling mechanism, and that does a pretty good job of giving you confidence ratings that come out of this. We'll see that in a second. But there are other techniques, including ones that we introduced in this paper, that are based on what I would say the concept of robustness. One of them that we did not invent, k-nearest neighbor classification, simply maps every test stimulus onto some reduced multidimensional space of all of the training examples it has learned, finds the nearest ones, and then scales its confidence on the basis of the proportion of those that match the majority vote. Pretty smart strategy. It's a measure of robustness to perturbations in that feature space. Also, we're going to talk a little bit about image blurring, which is simply a method of resubmitting the same test stimulus over and over to the agent, to the AI system, and seeing the consistency of the responses. If under extreme blur or if it under different blurs generates a lot of different answers, that translates then into lower confidence. And though, oh yeah, I think this is mostly what I just told you. There's how k-nearest neighbors works. Consensus is a measure of robustness. These input perturbations, we can see we're using salt and pepper noise in the top example and luminance graded noise. This is a cat-dog discrimination task for the agent. We then look at the same kind of calibration plot that I showed you a minute ago with the humans, but these are scaled from the network itself, and we can measure the expected calibration error of those. We also can look at receiver operating characteristics, which are a measure of the ordering of these confidence ratings. Do higher confidence ratings reliably predict better performance than lower confidence ratings, independent of the values that those take? And when we take these two measures together, what comes out is that the methods that work best are the methods that are based on robustness. So that includes the k-nearest neighbors and the coherence methods that I told you about, like the image blur. One of the additional benefits of that, I think maybe I say this on the next slide, yeah, is that they work great. I don't say this on the slide, but they're also super scalable. They work for lots of different kinds of networks. They work for any number of items in the output layer and things like that. It's really easy once you've implemented these for small networks to generalize them to large networks. Okay, so now we have a strategy for scaling confidence that turns out to be pretty well calibrated from these types of networks. We have a theory that says, well, partners that are calibrated and convey confidence tend to be better partners, and we can expect them maybe that human AI teams that have calibrated AI partners will do better. And that's the last piece of what I'm going to talk to you about. This is a new study. The task is to estimate this is a perceptual density estimation task. So you see a grid like this, it flashes on quickly, it goes off. Some proportion of the squares are filled in black, and you just have to estimate what that proportion is. I think this example is 50%. Sorry to ruin it for you. The human makes a judgment. They make a confidence rating. They then get a response from an agent that gives them the agent's estimate of what it thinks. That agent also provides a confidence rating, and then the human, just as in a sort of traditional judge-advisor system kind of, gets to change their response if they want to, and they move on to the next trial. And because we're psychologists, they do this like 400 times. Now the manipulation is, this is the new part, there are two different agents that different subjects get. One agent is calibrated, where their confidence is predictive of their accuracy. The other agent is uncalibrated, where their confidence is not predictive of the accuracy. But importantly, both agents are equally accurate. They are providing the exact same estimates on a trial-by-trial basis. I mean, it's random, not really on a trial-by-trial basis, but in the long run, they will be. But only one has calibrated confidence assessments. Okay, first, when you look at just overall performance, thank you, people do better on their second judgment on their first, not surprisingly. They're getting information from the agent. They do a little bit better on that second judgment when they're working with a calibrated agent. But we can zoom in more on what exactly is happening by using a good statistical model for this. First, we compute the weight of advice, which is simply a measure of how much the human response is moving in the direction of the agent's advice. We then fit this to a 0-1 inflated beta distribution because there's lots of zeros and lots of ones. They often ignore the advice. They sometimes take it wholesale. And then in the middle cases, they integrate. And the interesting thing to see here is that for any of these metrics, the calibrated agent really leads to a lot better teamwork. Human partners are way more likely to adopt the agent's advice when it's calibrated. They're way less likely to reject it. And when they integrate it, they take it more into account, and it has a greater weight in that integration. Okay, that's what I just said. Okay, I'll just briefly mention, though this is mostly just a tip for anyone who's interested and wants to talk about it later, that ZOIB model is a fun statistical model. It's not a particularly useful cognitive model of what people do. But there's lots of ways of taking standard models like random walk models that are commonly used in psychology and bringing it to this kind of task. In this case, we can think of the random walk as a choice between selecting one's own original judgment as the final answer, selecting the agent's judgment as the final answer, or reaching a point of indeterminacy where the point at which you end up actually determines the integration parameter of how much you're going to average those two responses. And off to the right are some showing you that even without working very hard to fit this model, you can get it to account for all of the effects of confidence pretty easily. Okay, I will wrap up now. I'm going to read off this screen. So I showed you three things. One is that human group performance benefits from the exchange of metacognitive information. It's not just about more knowledge. It's also about the exchange of metacognitive information that lets people work together. Two, it's relatively straightforward to get networks to give you confidence assessments in their knowledge if you want them to and they want to. And you can use robustness to perturbation as a good place to start for doing that. And finally, agents that have these metacognitive capacities, when they work with humans, end up yielding better performance as a team. Okay, thank you very much.
Thanks. Cool talk. Thanks for sharing this. Question about that last study. I think it was Deng and Benjamin. Participants knew that they were interacting with the advice of an AI agent. Is that right? Yeah. Any reason to expect any different results if they were, in fact, or at least believe that they were interacting with a human counterpart who's giving identical responses? In other words, have we learned something about how people collaborate with AI agents, or just how people respond to calibrated versus miscalibrated partners?
Yeah, I don't think there's anything particularly, there's no special sauce to it being an AI agent in this case. You know, we're doing it that way because then we can control its calibration. But there is a small literature. I'm not really an expert on this, but there is a small literature on the types of errors that people are willing to forgive from other people versus the types of errors that people are willing to forgive from AI. Right. So in the algorithm aversion literature, he says AIs. One of the things that's funny about them is that when they make a mistake, you've seen a couple examples that say they often make a mistake that you wouldn't make, and that's particularly unforgivable for us. Like, all right, this guy's really dumber than I thought he was. So, in a task like this where it's so oversimplified that there aren't really dumb errors and smart errors, I don't know that you could see something like that. But if you scale it up to the kinds of interesting things like medical diagnosis that we're hearing about, then I bet you could get nice differences between those types of groups.
Let's thank our speaker one more time.